Thank you. I'm going to be telling you some introduction which some of you have already heard, but those who haven't, please stay with me. It's the last talk of the day, so I'll try to make it easy to understand, and then we'll go for the dinner. This is going to be based, some of the results today and tomorrow, the new ones, on work with David Gossett, Sean Halgren, and Sandeep Narayanaswamy. But mainly, I want to thank some of the people that are here, that I can be here and giving this talk. This was from a hike that we did in Benasque this summer. Okay, I'm going to be talking about the onion and the little layers that are complexity, and specifically about one layer that's quantum, Merlin, and Arthur. And I'm going to be focusing today on the problem called local Hamiltonian. First, I'll try to answer, or to motivate why I actually want to talk about Hamiltonians, give you a little introduction to complexity, and then go on what the QMA is, how it is connected to finding ground states of local Hamiltonians. And then, when we have time, we will look at whether these tricks and funny things can be done also in one dimension. And what we'll leave for tomorrow is going to be the class QMA1, and it's going to concern problems without frustration, with when we are going to verify some solutions to problems, we're going to be able to verify them perfectly. And specifically, the problem we'll focus on will be quantum satisfiability, and in particular, quantum 3-set, which we have recently proved that it's QMA1 complete, and then also random instances of quantum set and phase transitions in that, and possibly we'll have time for quantum PCP. So let's go into what we have on the table today, and that's going to be Hamiltonians. Hamiltonians are things that describe interactions in quantum systems, and one of the things it describes is dynamics. And we would like to be able to simulate quantum systems, and that can be hard. We can get in pictures like this from Fermilab, or possibly something that connects to quantum walks and algorithms, what Miklos' talk was recently, and one of my favorite results of this year. If you were able to solve scattering of a quantum walk of several walkers, you will be able to do whatever a quantum computer can do. Next thing what you can do with Hamiltonians is you can ask optimization questions. How hard it is to find the best possible and squeeze the configuration and squeeze the energy down as little as possible. How do proteins fold? What's the best configuration? Or possibly what's the best configuration for spin glasses in condensed matter? All of these systems are governed by local Hamiltonians, with which I mean that every particle interacts only with a few possibly neighboring particles at a time. Although mostly what I'll talk about today won't really have physical neighbors, but only, for example, Honza knows only 3 people in this room, and Minsu knows just only a few. That'll be fine. And there will be people that are connected to almost everybody. Okay? But I don't really want that much. I would want everybody to be connected to only a few, possibly a constant number. And only a small number at a time. Okay, so these are the Hamiltonians. One of the reasons why these problems turn to be hard, or seem to be hard, is frustration. For example, when I have this antiferromagnet with interactions like these, there's just no way that I can make everybody happy. There will always be some configuration that will be unsatisfied. So they just have to point in the same direction. And so it means that when not everybody is happy, the ground state of the system is going to be a global ground state. It's not going to be a ground state of every term at a time. So then, possibly, it could be very entangled and might be hard to describe it, and it also might be hard to find it. Maybe in some systems not, but in some systems it does. And we are left frustrated. Here are local Hamiltonians. It's a Hamiltonian that's a sum of terms, where each term acts only on a few terms at a time. So we can look and try to find their optimal configurations and ground states and ask questions about the ground state energy, or possibly even do it at a higher temperature and look at different observables. And these things, questions about ground state energies, are connected to QMA complete problems, which is what I'll explain what it is in a bit. Second, once I imagine that I have such a Hamiltonian, I can do something with it. I can build a computer. I could possibly simulate quantum chemistry or solve control or transport problems. And one of the ways that I can use it for is, or the keyword would be BQP universality, whether a Hamiltonian or with a particular class of Hamiltonians is suitable for making a computer. And I'm going to be making distinctions or trying to optimize in all of these different ways. So that's a local particle dimension. So that means like how many states can you be in? possibly how many other things you interact with, whether the interaction stays put or whether it actually changes in time, and then whether everything looks the same whichever way I look at the system, whether translation and variance, whether the Hamiltonian itself comes with a promise, so that I already know about something about it. I'm just supposed to distinguish two different Hamiltonians possibly, and then also how strong are the fields, for example, that I'm trying to apply to my system. Let's talk about complexity. Complexity tries to answer the question how hard it is to ask a question. One of the basic complexity classes is the class P, and it's the class of problems that we just can't do. The second class of, for example, like this, I can ask you, can you draw this picture with just removing your pencil from the paper? And if you're starting to get bored, please go draw this and that. Right? You can answer these questions easily because it's calculable. Yeah? Okay, you've got it. Great. The second class of problems that I'm going to talk about is the class NP. And it's the class of problems where they're probably turn to be a little harder to solve. And if somebody very smart comes and tells me the solution, you tell me how I should go, then I can check it. And I say like, yeah, this is exactly the way that I should go. So these are the class of problems where you can verify a solution easily. But maybe finding it is not that easy. This is one of the problems in this class. That's the graph isomorphism. So are these two graphs isomorphic? So just take, stretch, move them around, and tell me whether they are the same or not. Okay, your mind is getting stretched. And now I give you a hint, right? I'll give you a hint. Just kind of like invert it out. Do you believe me now? Okay. So these graphs actually are isomorphic. Another type of puzzle. This is the cryptarithmetic. There's a website called Read IT Crypterm something, and you can just try to come up with words and see whether something makes a puzzle. So try to replace these with numbers, and if it works out, you found a solution. And I'm asking, does this puzzle have a solution or not? And then if I give you the answer, you'll be able to verify that it actually works. These are problems in the class NP. And the protocol in general goes like this. I ask you, did dinosaurs exist? And you bring me a proof, and I'll just believe you. Or possibly not a proof, but maybe just a witness, somebody who has seen it and who I can trust and I can believe that. Okay? These are yes-no questions with easy-to-verify solutions. The basic tool there is a verification circuit. It's a circuit, it's a computation that comes from a uniform family of circuits, meaning that it's not very different from different sizes of input. And here comes a witness, and then if the answer to the question was yes, I will be convinced. And then if the answer to the question was no, no matter what you feed me in, I won't accept. So this is the class NP. Now, if you didn't tell me anything, this would be the class P. So the things that I can do by myself. I will just calculate and then verify my solution. So I'll just figure it out by myself. But for NP, somebody has to give me, or somebody could give me the proof, and I will accept it. Now, what's the hardest problem in this class? What is the mother of all questions in NP? That would be an NP hard problem. This problem I can imagine is, could this circuit ever accept an input? Or meaning also, could this circuit ever output 1? So this is some verification circuit. And one of the ways that I can translate it into another problem is that I will put bits on each line in the circuit. And this circuit only involves like gates that have like 2 inputs and 1 output, or 1 input and 2 outputs, and whatever, something like that. So I can write down conditions that S must be equal to X and equal to Y. I can write them in a conjunctive normal form, and they can be written as 3 local conditions. So I'll write a condition on these 3 bits so that they work as if X and T were inputs and Z was an output of a gate. And also I can write a condition that W just has to be 1. And once I have this problem and I ask you, does a string STXYZW exist so that all of these conditions are met? Answering this question would tell you there exists a witness on which a correct computation runs and outputs a 1. So this verifier circuit could accept something. And that's the Cook-Levin theorem, or one direction of it, that 3-set, so 3 satisfiability, or answering questions about Boolean formulas that involve 3 literals at a time, is NP hard. Because solving 3-set could help you answer anything in NP. And also, 3-set is in NP, because just if you give me a string, I can just verify, is it a correct calculation or not. So then it's together, it's NP complete. One of the problems that is NP complete is the Hamiltonian cycle. So look at this board, take the chess horse, and go around it, and end up at the same point where you started and visit every point just once. And again, if these things are very simple for you, just go and play with this puzzle. There is a way of doing this. We're going to other puzzles, the puzzles of QMA. So we're starting to go quantum. This was a classical computer. Imagine that what we're going to do and try to solve is going to involve possibly a quantum computer. So instead of having P, we're going to have the power of quantum. So with NP, we were getting a witness, and we're going to accept it. Now, I want to do one more thing, because the quantum computation is somehow intrinsically probabilistic. So I'm going to ask for a proof, but instead of a proof, I'm just going to get something else that maybe will not be accepted like immediately, and I will have a chance of checking it. I will be eager to be convinced, but maybe there will be a chance that I will reject a good thing. And also, if a false thing comes in, maybe I should not be fooled, but sometimes I will be fooled, because my check will be also just probabilistic. This is the class MA. So the class MA is when something good comes, I'm likely to be convinced, and when something bad comes, I'm likely not to be fooled easily. There has to be a difference between these two things. And if I make a probabilistic check, sometimes I will accept a bad proof, and sometimes I will also reject something that's genuine and good. But that's fine, as long as these two probabilities are separated from each other. Now, this was a probabilistic check. Now I'll do something similar, probabilistic, but with a quantum circuit. So imagine that I will replace a verification that throws in some randomness with a quantum circuit. So here's a unitary operation, and I'm asking the question, does a witness exist such that I will measure a 1 on the output? There's something wrong with this picture. There's something that makes it too easy. So could you produce a psi on which the output would be 1? Could you do that for me? What would you do? You can do it, just make it up, or also run it backwards. Okay, so I'll just put in ones and prepare some phi, and then I'll get the ones. Okay, so this is a stupid class. This is not how it works. So one thing that I need are ancillas that are initialized as 0. So then whatever I feed in, and I just run it backwards, I won't be likely to get zeros here. So this is just a security check. Now this is the QMA protocol. You get a witness and ancillas. You run a quantum computation, and you measure an output, and you either accept or reject the input. And the problem is in a class QMA, if you can accept a good proof with a large probability, and you don't accept bad proofs with probability higher than some b. This is QMA. And now I'm going to ask the similar question as we had for NP. So what's the mother of all problems in QMA? What's the hardest question? And the question goes like this. Can we feed something to this quantum circuit so that the output will be 1? And we're going to try to translate it into another problem, just like we did classically. So classically, we translated the computation on wires into bits. Here we want to do something similar. But it won't be that easy. Because a quantum computer and a quantum computation runs according to a Schrödinger equation with some Hamiltonian that's made out of possibly local terms and generates a unitary time evolution. And now I would want to use this to implement some unitary circuit. How do I make my system compute and calculate something? One of the ways would be to just imagining having a system and like making little cuts where I start with an initial state, and after each cut it will be something that's already evolved. So for example, in the tth column I would get phi t, which is already t gates applied. This, I could imagine, could produce a state like this. This is just an analog of the classical construction. However, this does not work. What's the problem with this? This is too powerful. I cannot hope to make something like this. What's the reason for that?
Cloning.
Sorry?
Cloning.
No cloning, exactly. Because if I did nothing here, so phi t would be just the phi 0, it would create phi 0, phi 0, phi 0, phi 0 for me, for free. Or maybe for some work. And this just cannot work. So I cannot imagine making a construction like this. So even though classically I can copy and I can cut, I cannot do this here. There is one way to solve this, and I would really want to find other ways, because we've been playing with this one way for quite a while, and that's why I'm just giving the intro. And this way is a Feynman's computer. Feynman's computer runs like this. It goes and takes a system with two registers, with control and with workspace. And in the workspace, you work hard, and the control just goes and moves you whichever way you want. So it goes like, okay, that direction, this goes in that direction, and sometimes the computation is done. You can imagine a quantum system doing this. So there's one register here. There will be a clock and another register that's called work. And this is the Hamiltonian. The Hamiltonian, what does it do? It takes the clock register that's in a state t minus 1 and brings it up to the state t. So moves it forward one step while doing something to the data. So if I'm the clock and you are my data, as I move forward, I compute on you. I move forward, I compute on you. And then here, the other term, the Hermitian conjugate, is when the control moves back, I uncompute. And I move back and I uncompute, possibly on a different data qubit. This thing generates something that's called a quantum walk on a line. That's just the very simplest example of a quantum walk, although in continuous time, where if I have this state, what other states could this Hamiltonian generate for me? Will be superpositions of states, but the basis states will be like this. Just a single gate applied to the data and the clock moved forward. Then two gates applied and the clock moved forward, and so on. And these states are connected by the Hamiltonian very nicely. Because if you imagine just multiplying this guy by hf, you will go up, up, or down. And now if you just make a simulation of it, this just goes and moves, makes a superposition, and ends up, or just keeps running because it's unitary. It doesn't even really spread. Goes between two endpoints. One of the points, it was the original initial state. It might even return back to that state, possibly. And the other state is the state at the end of the computation. And if you manage to measure, and like as the control is moving in the system, find me here at the end, then you know that here, in the data register or in the work register, the computation is already done. So that's the way that Feynman managed to make a computer out of a Hamiltonian. Now we're going to use this to generate a hard problem. One more thing, when you have this line of states, and this is the Hamiltonian, how does the Hamiltonian look as a matrix? This is something pretty simple, just because it connects states up and down, so it's off diagonal once. You can even imagine wrapping it around on a circle, and the eigenvectors will be plane waves, or just their linear combinations. So we'll be able to solve everything, and the dynamics, everything is fine there. Together with Kitaev's ideas, we'll be able to translate this now into a problem called local Hamiltonian, which is what I want to talk about today. And the problem state goes like this. Is the ground state energy of a Hamiltonian that's made out of local terms very small, or is it higher than some level? And I would like to be able to answer this question. For example, if you knew how to prepare ground states very well, you would be able to answer these questions, and then you would be able to answer all the questions that seem to be hard, or many of the questions that seem to be hard for quantum computers. And that would be too powerful. And that's why people are trying to get numerics and simulate quantum systems, and they sometimes hitting walls. What Kitayo did to Feynman's Hamiltonian is that he created a Hamiltonian for which the uniform superposition over the whole history of the computation, so the superposition of this, this, and that, is a ground state. This is called the history state, where you should be able to expand that this phi t, which you already seen in Fernando's talk and in Toby's talk, is the original input with t gates applied. And now I'm going to look for a Hamiltonian which, when applied to the superposition, will give me 0. And it will be a positive semi-definite Hamiltonian, so this will be its ground state. Let's find it. The way we're going to do it is that we're going to write k local conditions, or we want to, which check whether the clock register is proper, because the clock register also needs to be some physical system. Then I need to be able to check state progression. So when I have a state of this form in my superposition, in my ground state, there needs to be the next state right after it. And of course, I'm going to write terms that it means if there's this guy, there needs to be the next guy, and the previous guy, and so on. Then I'm going to write terms which are going to check whether originally in the initial state, the ancillas were properly initialized, which was what I needed for QMA so that it's powerful enough. And then I'm going to write another term which is going to check whether the output was accepted or not. This is how I'm going to do it. This is a nice basis of states. Now, if I write Feynman's Hamiltonian that you've seen, that just connects these two states, turns one into the other, and I'm going to add a couple more terms that let them be, but notice this minus, together when I apply this Hamiltonian to this superposition, what will I get? First, this term applies to this guy and turns it into this one. Then the blue term applies to this guy and turns it into the previous one. However, they have opposite sign, and together they will give me a 0. Similar, these guys join, and they'll cancel each other out. So this Hamiltonian, in this basis, how does it look? These things make cross terms, and these things make them stay the same. So it's a project. It actually turns out to be a projector. It's like 1 minus sigma x. So it has eigenvalues 0 and 1. And it's nice. And when I'm going to connect all of them together, altogether I'm going to get an tri-diagonal matrix like this. One more thing. You can also rewrite this Hamiltonian in this form, which is a projection onto antisymmetric combinations of these states. Which basically says, I hate antisymmetry, so when there's something, I want to have a symmetric one as well, if I want 0 energy. And anything that doesn't have the symmetry, the energy goes up. The eigenvectors and eigenvalues of this are plane waves, or their combinations. If you want to solve just for a walk on a line with edges, it's easy to make it out into a circle and enforce that there are zeros here and there. And you can do this. It's relatively easy. And then the eigenvalues, they make a spectrum, and the smallest gap is 1 over L squared. We're going to remember this for later. But still, we're not done, because we only checked progression, and the t stayed under the rug. So we're going to take it out and make sure that this t can be written as a lock state that can be checked and looked at and progressed locally. Like this control was a single particle that was just moving and making sure that just only one thing is active and can move to the next spot. So we're going to go and have a clock workshop. The first thing that Feynman had was a pulse clock. So the clock that encoded a time t in the control was just a single particle that was hopping on a line like this. Of course, it does it in superposition. I'm just showing little photographs of it. The transitions in the system are too local, because if you are an active particle, and then you can look, is there a spot in front of me, and then you change spaces. So the transitions for this clock are just too local. What's the projector that I need to write down so that superpositions like this are preferred, have zero energy, and anything else has higher energy? This projector looks like this. It's a projector on the singlet. Okay? So, which means that a state that contains something like this can have zero energy only if there's the next guy as well. Like this. Now, imagine I have this clock, and I want to also do the computation. So this is the control, and here's my data. And I want to do, for universality, I need to do 2-qubit gates. So I need to go, as the clock moves from here to here, I want to, for example, do a control knot on you two guys. So that's 4 local. And that looks nice, but there's a problem. There's a state like this that's just dead, that doesn't have any control, and the stage is empty, and this guy is a ground state of this Hamiltonian, and nothing happens. So this is not a good clock for doing this QMA construction, because it needs initialization. But then Kitayo came up with a different clock that's really simple, and it's the domain wall. So a domain wall is like this. It's just spins that are active and spins that are not active, and they are moving forward or back, and encoding time like this, in unary. How many qubits do I need to look at to progress this clock? To make it unique. Go like from here to here. It's not enough to look only at like 2, because if I go forward, then any 2 that are 1s could move into a 1-0, which means, like, for example, this one could turn itself off. So I really need to go with 3, like this. And then also, what is the way that I can enforce that my clock register will have this form, the form of a domain wall, so with 1s and 0s? What is a projector that's compatible with this and incompatible with everything else? Yeah, penalize 0, 1, exactly. This is the one that will enforce something like this, and you can also then fix the first one to be 1 and fix the last one to be 0. And then you're sure that there is a domain wall somewhere in your system if the energy is 0. So that's the nice thing. Now, the transitions, we just said that there were 3 local, and you can enforce them by a projector like this. So this is a projector onto the antisymmetric combination with these triplets being 1, 0, 0, and 1, 1, 0. And that's our domain wall clock. The ground state of the domain wall clock is just, again, a uniform superposition over all of the clock states. When I want to interact with the data, I have these 3 qubits that I look at in the clock and 2 qubits in the data, and as the clock progresses forward, I do an operation. And that's 5 local. And this is now the Hamiltonian that I had. I can rewrite, instead of these t's and t plus 1s, I will just write these small 2 or 3 qubit things, and these 2 will be just 2 qubit things. Altogether, it will be 5 local. And it will work well for good clock states. And anything that's a bad clock state that has a higher energy, so I won't care. And the candidates for ground states will have to have good clocks, and on good clocks, this works as advertised. So altogether, 5 local Hamiltonian will be QMA complete. When I finish the 2 more things, one thing, I will check whether the initialization was proper with a term that when the clock was just at its very beginning, so 1, 0, 0, 0, 0, 0, then the ancillas had to be 0. If there were 1, the energy would be up. And I will punish computations that did not accept. So when the clock was at the end, then the output qubit had to be a 1. And this I will do with a projector that when the last qubit is initialized in the clock, or maybe 1, 0 here, then the output qubit has to be 1 for this to have 0 energy. Altogether, this takes my Hilbert space, and if the answer to my problem was a yes, if there was an accepted computation, there will be a ground state where everything will work, meaning that the Hamiltonians applied to the history state of the computation on this ground state will just give me zero energy. On the other hand, I need to show that in the case that there is no nice computation on a very good input state that will be accepted, then the ground state energy of this Hamiltonian has to be high. And this is how we're going to show it. First, we divide our Hilbert space into a space of the bad clocks and the good clocks. We just can continue thinking about the good clock states. We're going to divide those into states that are history states that have uniform superpositions and states that don't. You can forget about those. Inside the good history states, inside that space, I will have a gap that goes like L to the minus 2 that comes from how the Hamiltonian is connecting them. So these are history states and also states that have like just slightly different phases. Now, I'm going to divide that into a space that are history states of states where they were properly initialized and improperly initialized. Then I'll forget about those, and now I have well-initialized histories. And then there's another subspace of accepted states. But these are orthogonal. And now what I will do, I will look at my Hamiltonian, and it has two terms. One term that is 0 only here, and another term that's 0 only here. And they don't overlap. And I will be able to bound that their sum has to have lowest eigenvalue at least sine squared over between the angle of the subspaces and the minimum gap within these subspaces for these Hamiltonians. And we already showed that this gap was L to the minus 2, and the angle can be shown that it's L to the minus 1. And altogether, this will make local Hamiltonian, or 5 local Hamiltonian, a QMA complete problem. This is how we translate it. We had the verifier circuit for a QMA problem. On the other side, we made a Hamiltonian for which we thought of the history state as a candidate for zero energy or very low energy state. Now, if the answer to this problem was no, meaning that there was no witness that I could feed in that would output 1 with probability greater than epsilon, it meant here that any state for this Hamiltonian had energy that was at least some number that was lower bounded by 1 over L cubed, but still something polynomial. On the other hand, if the answer was yes, there was a way to feed something in here that the answer was yes, accepted with probability very close to 1. And there it meant that when I feed the history state of this to this Hamiltonian, its expected value of energy will be just something that goes down with epsilon. As epsilon goes down, these two things separate, and this will have low energy or higher energy. The answer was no. So we end up with local Hamiltonian being harder than anything in the class QMA. Also, local Hamiltonian belongs to the class QMA because I can just give you the ground state and you can measure the energy and figure out that it was low, and I can convince you. There is a circuit for that. So this is my local Hamiltonian problem that has a low energy, ground state energy in yes cases, and has a higher energy in the no cases. And this is what's called the promise gap. There are two gaps that move around in these problems. One is the promise gap, one is the eigenvalue gap, because this is the eigenvalue gap of the Hamiltonian and eigenvalue gap here. Sometimes, or we've seen in the previous talks, or Fernando was definitely talking about it, when we have a gapped Hamiltonian with a constant gap, we can prepare the ground states. So now the question is, how big could the gaps possibly be so that the problem remains hard? We are trying to make this promise gap harder because it means that I cannot make measurements up to some precision because they will be just hard. That's kind of weird. And also, could these gaps be made bigger so that it would be tantalizing to think that I could prepare the ground state myself? And that's what people are working on. Trying to even make this promise gap bigger, that would be the quantum PCP theorem. Okay, there are other QMA complete problems. There's a good review by Adam Bukatz. One of the problems is, for example, there's a unitary. Can you feed something to this unitary so that it makes it into a separable state? This is hard. Second problem is, I give you a unitary circuit, Does this circuit do anything? Is it any different from identity? This is a hard problem. Another problem is matrix consistency. So I give you local density matrices, and I ask you, can you make a state out of these local density matrices, or do these local density matrices come from a state? That's hard. Another, I actually shouldn't have written complete, I maybe should have written just hard. Another one would be figuring out the density functional potential in quantum chemistry. There are many, many others. You can look into this paper. But sadly, there are not as many different types as there are NP-complete problems. So we're always looking for new ones, and you're welcome to do that. What's the status of where we are at in the variance of the local Hamiltonian today? So we're looking for a global minimum of a sum of terms. And it's been proven by Roberto Oliveira and Barbara Terhal in I think it was 05, that a two-local Hamiltonian with qubits on a 2D grid is already QMA complete. And similarly, on a line, or very unsimilarly, in a different way, when you have a line with qubits that have dimension 8, then this is also QMA complete. And maybe when we'll have time today, I'll actually go and tell you a little bit about this. This is a recent result with Sean Halgren and Sandeep Narayanaswamy. How do you go from 5 local to 2 local to something like this, or even 2 local on a line? The way to go is that for the domain wall clock, we looked at 3 qubits at a time to progress the clock. Well, what if I just look at a 1 qubit at a time and just make it turn itself on? It seems like it's working, but this guy could turn itself on and create a state that's illegal. But what I will do, I'll just hit it with a very big term, like this. Meaning that if any time this appears, it would necessarily have high energy. So then, things that would be proper clock states would not necessarily be eigenstates, but will still stay low energy states, and these guys will just disappear. Or will just be in a subspace with higher energy. This next thing, that what could, or how it could have worked, that anything that got bad, like any bad transition, got punished right away. It means that when the history state originally was a ground state and an eigenstate of the 5 local Hamiltonian, now when I have this Hamiltonian that also has terms like this, where something can turn itself on and off whenever, when there's a history state, it takes it to a state that doesn't find its partner on this side. So altogether, even for this Hamiltonian, the history states will be 0 energy states. And that's a very important property here. So that like bad transitions are immediately detected. And now when you make a gate, so I have a term that looks like this. This will be now 3 local because it's a 2 qubit gate and a 1 local transition. This could happen, or that could happen. And again, I just hit it with this guy, meaning that this would have higher energy, so it actually will disappear, or have high energy, and only these things will stay in the candidates for low energy states. So 2 qubit gates can be also done 3 locally, and one of the reasons why I could do this big time hitting was the projection lemma. So this is a very useful tool, which when I have a Hamiltonian that's really big, so has high norm and then also like the gap is big, so I have a subspace where this Hamiltonian has 1 eigenvalue, say 0, and then another subspace where it has a much higher eigenvalue, and then I add a little term to it. The spectrum of this Hamiltonian is going to divide into little things, but the projection lemma that's stated here says that when there's a very high penalty in this subspace, then the low energy states must live very near this subspace, where the H2 had 0 energy. It says that the actual eigenvalues are close to the eigenvalues of this little Hamiltonian restricted to this subspace. And that allows me to prove many things. So, for example, even though the Hamiltonian H1, which was these 1 local transitions that could appear at very different unexpected times, they actually won't, because this would be in this subspace that has higher energy, and the actual eigenvalues and eigenvectors would belong to this subspace where the Hamiltonian is behaving properly, so only in proper clock states. So then this type of operator really will just restrict it to the subspace, will look like as if it was the 5 local one, and that one also restricted to the proper clock states just looks like the one that I actually wanted. That was the T, where the T was the clock state, not just whatever, 1, 0, whatever. Now, so I turned a 5 local Hamiltonian into a 3 local one. I didn't do that. That was Julia Kempe, Oded Regev, and Alexei Kitaev. And now this can be turned into a 2 local Hamiltonian by changing 3 local interactions into 2 local interactions and making the 3 local effectively. So you introduce new qubits and you introduce really strong interactions between them so that somehow if you change something here, you would want to flip this guy, but this guy won't go by itself. It really will flip those as well, and that will affect those guys. So this guy, through these intermediaries, really feels both of those. And that's how you can make an effective 3 local interaction out of really strong 2 local interactions. So this ended up being a 2 local Hamiltonian that's also QMA complete. And then finally, this has been turned down into 2 local Hamiltonian on a 2D grid by Oliveira and Terhal in 2005. And the way they did it, they took a 5 local Hamiltonian and made it spatially sparse. So they actually spread the qubits around and made them move a little bit. And then they took these 5 local interactions into 3 local interactions, and then they introduced new gadgets slightly different than those so that they could also spread it out in 2D. And that's the end of the story for the 2 local Hamiltonian at the moment in 2D. One of the things that we would like, could something like this be done without these gadgets, or in a way where really we wouldn't have to introduce like 2 or 3 more energy scales for punishing these bad states, but something that would come more naturally. And that would be interesting. So this is the end of the local Hamiltonian. One of the things that we have done, we have seen several clock constructions. One of them was used in the Kempe-Kitaev-Regev papers, and that's a control that's moving and something happens to the data. In other papers, like in Ari Mizel's universal constructions, or in, for example, the adiabatic papers of the universality of adiabatic computation by Dori Dahanov and others, the clock has a geometric feel, meaning that there's data, like imagine that you are in the first row, you're the data, and as the computation goes, you have to go and switch to the next and to the next row, possibly in a synchronized way. So this you can do, but you need maybe higher dimensional particles, because for example, the particle here on which Honza is sitting could be like an empty chair, and a Honza with a qubit that's a 0, and with a qubit that's a 1. That's already at least 3 dimensions, and that could be more. Now you can imagine that here, like these clock qubits these data qubits were connected to many different clock qubits. So this is not really geometrically local, but you can make the best of these 2 worlds together and make it geometrically local like this. Imagine that these are the data, and the clock qubits are kind of winding around. So the clock progresses this way and helps compute, and as it goes back, it moves the data forward. And then it computes and moves the data forward, computes and moves the data forward, and computes. So this way, winding around, you can make sure that every qubit is interacting only with a constant number of other qubits. Okay? So this is geometric locality. And finally, you can take this and make it work in 1D. So I'll let you observe this, like how is this working? This is, you're taking the data, like here was the data that I wanted to compute on, and I want to move the data on a line. And the data moves on a line with the help of a hat, which is like go pass the hat to the next person, put it on the ground, jump over it, and kick the hat back. And this is the way that you can move qubits on a line, or move data on a line. Of course, the construction is a little more complicated, and we'll get into that probably tomorrow. I'll just give you a little feeling of what can be done in 1D. Local Hamiltonians in 1D. One of the things that works very well are matrix product state methods. So when I have Hamiltonians and I look for the ground states, Condensed matter physicists love this. They do DMRG in one dimension very often. It works even at phase transitions. It's a very nice numerical method that's based on a low entanglement ansatz. When I have a state that's a generic superposition, I can do Schmidt decompositions and cut it apart into a product of matrices, and then this gives me a nice approximation if the size of the matrices is not too big. And if the entanglement is low, this works nicely and gives me a local optimization method. With the help of these, we can think of solving, for example, chains of qubits. And in fact, we know that the quantum two-set problem, that's not the local Hamiltonian, but that's the unfrustrated version, is easy for qubits. For a frustrated version, for local Hamiltonian 1D, we actually don't really know. Next thing, when we use a very high dimension of the particles, so 13, 11, or later 8, this can be hard. This will be the construction with the heads. When I go even higher, when you have translation invariant interactions for 21-dimensional or 14, this can be, the states there, the ground states can be very entangled, going close to the areal or even beyond. Now, if you go even higher with like 2000s or something, then you will see something similar to what Toby had in his talk, and that's the construction of the Daniel Gottesman and Sandy Irani, where you have a translation invariant thing that's just very hard. We'll talk about it just a tiny bit. Then when you go to dimension 4, so Q quarts on a line, I can write Hamiltonians which have unique ground states that are very, very entangled, or even when I use random projections. So that's something weird. Here it's hard, here it's easy, here it's something intermediate, I don't really know what. In Q trits, we knew that there was a translation invariant AKLT model which had just a constant Schmidt rank. And I can just ask, are the ground states of these guys hard to find? Can they contain lots of entanglement? And for qubits, they can't. For qubits, say 11, they can. It could be really hard. And I looked at Q trits, and there we found a ground state that's very entangled and very intriguing. That's the bracket construction with Sergei Bravi, and Peter Shor, and Ramiz Movasag from last year. And then at 8, with Sean Halgren, we have proved that Q, 8, it's on a line, and the local Hamiltonian for them is QMA complete. I won't have time to really do this. I will slow down. We'll go to that tomorrow. But there are many open dimensions in between. So this is hard. This can make a computer. This is easy. This is something intermediate where we don't really know whether we can solve these problems or not. And it's fun to play with. And I encourage you to come and discuss and see what can be done. I'll give you a feeling a little bit more for the heads, for 13. So when I have imagine that I have a construction with a clock and a work. I would want the history state to be a ground state of some Hamiltonian. This was the propagation Hamiltonian that took one state and made sure that the next step was there as well. I'll try to write this locally. So locally, that these terms would act only on two particles that are next to each other. So for example, it would mean that when I have a state that has A, B in a superposition, and if it wants to be a zero energy state of such a Hamiltonian, it needs to have whatever it had here, and CD in the middle. In such a way, it would be a global ground state of the whole Hamiltonian and a local ground state of every term in there. And in a sequence of papers, it's been proven that it's actually, there was not 12, but 13, 11, and down to 8, that it's QMA complete. And the two local rules were making a construction like this. And I will just skip a couple things. No, I'll make them tomorrow. Have some fun there. And end up with, I wanted to tell you today about what QMA is. It's the class of problems where you can verify with a quantum circuit some quantum state that somebody feeds you, a quantum proof. Shown problems that were QMA complete, which meant that you can turn any problem in QMA into a problem like this. We have, now you should be able to tell somebody what a history state is. It's superposition over all things during a computation. Shown you a couple of code constructions, and basically in the end ended up with the local Hamiltonian problem, which was QMA complete. I really haven't shown that it's QMA complete in 1D. And tomorrow I'm going to continue with that and telling you more about the class QMA1 of unfrustrated problems. Thank you.
So early on, you mentioned a connection to universality for BQP. It's kind of going into it. Is there kind of a formal relationship between the two, or is it just, so far when we found that one thing is QMA complete, also we can build a quantum computer out of it and vice versa?
Okay, so Ashley is asking, like, when I have I mentioned a connection that you can use this, either the ground state is hard to find, possibly a QMA complete construction, or I could use this Hamiltonian to run a computation. Whether this is formalized, well, I don't think that we have something formal, but generically, if you have a Hamiltonian whose ground state is hard to find so that you can encode the computation inside the ground state, it very often turns out to be that if you just start with a particular state and evolve with that Hamiltonian, it will actually run the computation for you. So generally, if you have a Hamiltonian that's enough for a QMA complete construction, it is also enough for a computer. On the other hand, there are Hamiltonians which are enough for universality, but we don't know how to make Hamiltonians for them for which the ground state would contain the computation. And generally, those ones that are universal take like lower locality and lower dimensions and have nicer gaps and so.
Is there any relation between the two gaps, so the spectra and the promise, or any bound of one from the other, or vice versa?
Okay, so is there a relationship between the promise gap and the spectral gap between these things? So here, as we were doing things, in fact, we were able to show a promise gap because we knew that our Hamiltonian has some eigenvalue gap. So they actually were related in calculation in our specific construction. But it doesn't have to be so. Or we would really like to find something where the for example, the promise gap would be even bigger or much bigger than the actual eigenvalue gap of the Hamiltonian. Because we expect the eigenvalue gaps to be small. Because if they were large, we would be able to find the ground states, say by imaginary time evolution. So here, they were tied in our proof. And right now, we don't really know how to make them not connected. Because, in fact, it is, in the end, very often that we have two subspaces, and then we have something that works here and something that works here. They don't work together. But in this subspace, there's something else that's kind of like nearby that starts to being close to this subspace, and that could make a problem. So if we have Hamiltonians that have small gaps, then it's hard to expect that the promise gaps will be much larger.
But there's no proof that this should be in general like that.
No, we don't have anything like that.
Any other questions? If not, let's thank Daniel again.